by checking the box at the left to add the package to your current SolidWorks session. Okay, but we're going to use PhotoView 360 and SolidWorks Motion today. We'll look at a couple more next week. I'm going to click OK. And while that's loading, the scenario that we've got here in this assembly is we've got the egg lander model here, and we're going to position it up above the surface of the moon, and we would like it to have a nice smooth landing on the moon. Okay? So the way that we run a motion study is actually just click down here on the motion study tab at the lower left, which we've kind of been ignoring all semester long. And I'm going to click motion study. And it opens up a new timeline down here and a new model tree with some extra stuff in it. And this selection box right here lets me choose what type of motion study I want to do. Now, an animation is sort of the simplest form of motion study. It's not really motion study at all. It's really just a tool that lets you make a movie of your model, whatever you've got. You can put motors in it. You can do a little bit of animation with it. You can also set key points in your timeline if you want to show it in different, like if you wanted to zoom in at a certain time or rotate around or zoom out. You know, you can create a movie using the timeline down here and save that as an animation movie file. But the next option, basic motion, gives you a little bit more realistic simulation. Okay, so this lets you add in things like springs and gravity and motors and things. What we actually want is the motion analysis. That's the most advanced form of motion analysis. That's the one that lets us not only simulate what's happening and see it, but extract numerical results from that analysis so that we can determine what are the forces, what are the accelerations, and so forth. Okay, so motion analysis is the most advanced one. If you click this drop down and you only saw the first two options, that probably means you forgot to go to the tools menu and turn on the SolidWorks Motion add-in. Okay, because that add-in is what gives you this last motion analysis option. I'm going to click that. And the way that we run motion analysis is click the button right here that says calculate. Okay, so if I click calculate, you'll see it's running through the timeline, but in our model, nothing at all is happening. Okay? And the reason we don't see anything happening is because we've not defined gravity, we've not set up anything that would cause motion to occur. So one of the first things we need to do is turn on gravity. And we can do that by clicking the little button here that kind of looks like an apple falling through the air. Okay, it says gravity. We click the gravity button. We will choose the direction of gravity. And in our model, gravity should act in the negative y direction. So I'm going to choose y right here. And this arrow shows the direction that gravity acts in. And then we need to give it a value. So if this represents the surface of the moon, if I remember right, I think the moon's gravity is about 1/6 the gravity of Earth, right? Does that sound about right?
Yes.
Okay, so the value that we're going to use is 1.62 meters per second squared. Okay, so I'm going to type that value in with its units, and when I hit enter, SolidWorks goes ahead and converts that to the proper units for our IPS current unit system. Okay, so make a note of that. 1.62 meter per second squared is the value of gravity that you'll use. And I'm going to click the green check mark. So now we will click the calculate button and see what happens. Okay, so the egg's falling, that's good. But it just falls right through the moon and it keeps on going. Okay, it's way down here somewhere now. Okay, so the next thing we need to do is tell SolidWorks what things should act as solid bodies, what things should have contact and not pass through one another. So I don't know where the egg is now. I've lost it. It's down there somewhere in Neverland. But we can drag this timeline, the gray bar, back to the beginning to position everything where it started. And now what we'll do is use this contact button in our motion study. It's the one that kind of looks like a cannon follower system. I'm going to click that and scroll down. We want solid body contact. And we will select the things in our model that should behave as different solid bodies. So I'm going to click the surface of the moon, also the body of the egg itself, and then each of the 3 feet. Okay? I'm not going to bother clicking these intermediate linkages because I'm not concerned about those making contact with other things. Okay? So I just want to click the things that make them into contact with one another. I'll click the green check mark. Now, I will tell you something that sometimes causes confusion for people is they'll notice this play button right here, and they'll click that. If you click play, that's simply going to replay the last motion study you calculated, but it's not going to update with any changes you've made since you calculated it. So if I click the play button right now, and speed up the playback a little bit. Okay, the egg is still going to pass right back through the moon. It's not going to act as if contact exists. Now, it doesn't really show up on the big screen up there very well, but there's some great cross-hatching in this yellow timeline bar, and that is your hint that the motion study is out of date and it needs to be recalculated. So, I'm going to recalculate the motion study. Okay, so the egg's falling, and if we zoom in, okay, it kind of squats there, and still moving around a little bit, but that definitely was not a good thing. It just kind of smashed into the ground there. So now we want to add in some springs to make this a better suspension. So I'm going to drag this back to the beginning of the timeline and zoom into the egg. And we want to put springs on these intermediate linkages. So we have a button right here for creating a spring. We can do either linear springs or torsional springs. We'll do a linear spring, and we're going to select the surfaces that the spring acts in between. So I'm going to click on that surface and that surface. Okay, and we get this big old beefy spring. That's like the Arnold Schwarzenegger version of a spring. But we can tame that display down if we scroll down here to its display parameters right here. And let's just make the coil diameter about half as large. We'll make it 0.2. We'll make the wire diameter about half as large. Okay, so that's a more reasonable spring. But changing the display of the spring has no effect on its properties. Okay, if you want to change the properties of the spring, like make it stiffer or less stiff, you go back up to the section of spring parameters. Let's see if I can just drag this down a little bit. Okay. And up here is where we choose, first of all, do we want a linear spring or a nonlinear spring? So in your physics class, or maybe statics, you probably dealt with linear springs, right? Calculating spring force as force equals what for a spring? Kx. Force is a spring constant, the stiffness times the displacement. But real world springs can very well be nonlinear. So SolidWorks can analyze nonlinear springs as well as the linear springs. A nonlinear spring would have a force that's proportional to some exponent of the displacement, not simply kx, but it would be kx to some power. Okay, and then you can put in the spring constant, which is like the stiffness, and this value is the free length. So that's how long is the spring when it's not stretched and it's not compressed. By default, SolidWorks assumes that when you put the spring into your model, you're not preloading it. You're not stretching it, it's not compressed. It's going to measure the distance between the surfaces you act on or you put the spring between, and that's going to be taken as the free length. Okay, so let's see. Let's go ahead with that spring setting, and then I'm going each leg. So now, let's calculate our motion study again. We'll zoom in here. Okay. And we see it bounce, and bounce, and bounce, and it just keeps going. Okay, so that was 3 seconds worth of motion, and if we ran this out longer, it would probably just keep bouncing over and over and over. Because SolidWorks at this point assumes these are pretty much ideal springs, right? So in a real suspension system, besides the spring, what's the other main component? What else do you have in your car's suspension besides the spring? A shock, right. Some kind of damper to dissipate the energy. And that's what we need in our suspension system for the egg. We need a damper. Now there's a button here for creating and defining a separate damper, but we don't actually need to add that in as a separate component because in the definition of our springs, if I edit spring 1, there is a section for specifying the damping of the spring, because SolidWorks knows any real spring is going to have some inherent damping in it, and we can put in those values in our spring definition. So I can click the check mark next to the damper box, and again, you can do linear or nonlinear damping. And I'm just going to give it a value of 0.05. Okay. So, let's see. We said just a moment ago that for a spring, F is equal to Kx, right? Force is a spring constant times the displacement. For a damper, what's the fundamental law? Force is a damping constant, we'll call it C, times what? V. Times V. Times not the displacement, but times the velocity, or how quickly you're trying to expand or compress the damper. Okay, so, and I'll give you a hint, this is often a question that shows up on the next exam. Springs create force proportional to displacement, dampers create force proportional to velocity. And if it helps you to think of a kind of a real world example, you can think about like a swimming pool of water. Water is an example of viscous damping. If you go up to the top of a high dive and you jump off and do a belly flop on the water, it's going to hurt, right? It's going to sting, and that's because you're hitting the water with a higher velocity, and whatever the properties of the water are, times that velocity is going to exert a large force against you, and that's what hurts. But if you were to walk through that same swimming pool of water, and just walk slowly through it, the water still resists your motion, right? But it doesn't hurt when you're just walking through it. And the reason is, your velocity is lower, the water is the same, but the force is lower because of your lower velocity, okay? So, I'm going to put in a value of 0.05 for our damping, and I'm going to do that same thing to each of the other springs. And by the way, if you just type in a value and hit enter, the units on your damping constant can kind of also remind you of this idea, because if you look at the units of your damping constant, it's pounds force per inches per second. So it's a force per unit of velocity. Okay, so there's spring 2, and do the same thing on spring 3. Damper, 5. Okay, so now let's go ahead and calculate the motion study again. Okay, so the egg falls and it bounces, but it fairly quickly damps out that motion, so it doesn't just keep bouncing over and over. Okay, so what you're going to do in this motion study is modify the suspension of the egg lander by putting in springs and dampers so that the gold egg does not hit the landing pad, and you want to create a plot of the acceleration of the egg because acceleration is proportional to force. Okay? F equals ma. So we're trying to minimize the force, so you want to minimize the maximum acceleration experienced by the egg. And with a good suspension, as you play around with it, you should be able to get a value of around 1,000 to 2,000 inches per second squared. Okay, so let's see how we create a plot of our motion results. We're going to go to the little XY graph button for results and plots, and we're going to select a category. So you can do displacements, velocities, accelerations, you can do force, momentum, or other parameters. You're going to start with a displacement plot, and then you choose a subcategory. And the first one, I'm going to do a trace path first. So a trace path lets me select an entity like a point or an edge in the model, and SolidWorks will draw a line to trace out the motion of that edge that you select. Okay? So I'm going to do a trace path on each one of the feet. So there's the trace path showing the motion of the feet. And now let's do a plot of the acceleration of the egg. So I'm going to click the plot button again. And once again, we'll do displacement, velocity, and acceleration. For our subcategory, we'll do linear acceleration. And then we can either do just the x, y, or z component, or we could do the overall magnitude, which I'll do. And then choose what we want the acceleration of. So that's the egg itself, the body of the egg. Click the green check mark. Okay, and that gives us this plot, which we can resize. Okay, so if we replay the animation, so we've got this red line that kind of traces out or maps the point of the motion that we're seeing with what the value is on the graph. And if we, let's see, if I click back here and click on certain points in the graph, we can see where the motion of the egg was. So right there, if you look really closely, right there, there's a little spike in the acceleration plot, and that actually corresponds to when the first foot of the egg hits the ground. That shows up in our acceleration plot. And then there's this really big spike there where the egg itself bangs into the ground. And then beyond that, there's not huge changes in the acceleration, it's just kind of bouncing around. But in your plot, if you have a large spike, that's an indication that the egg hit the ground, and that's exactly what you want to avoid. So in a good suspension, you should have something that's not a sudden spike, but more like a kind of a smoother hump. And your value should be in the neighborhood of 1 to 2,000 inches per second squared, rather than about 14,000. Okay? Okay, so another useful thing is we can take this data and export it and work with it in Excel. If we right-click on the plot, you can say Export CSV. So you could export all the time and acceleration values to like an Excel spreadsheet if you wanted to do further calculations with them or plot them in other ways. All right, now, just for fun, let's change one leg of the egg lander and make it a lot stiffer than the other two. So I'm going to go to spring 1 and make that 10 pounds per inch instead of 1. And let's calculate that, see what happens. Okay, so the egg's falling. Okay, so that was the stiff leg right there. And we see the egg actually flips over, tumbles around, slides off the landing pad. And what's really cool is this is not just a little cartoon animation. This is all based on actual physics. This is 6 degree of freedom calculations. You've got translation in X, Y, and Z, and rotation about X, Y, and Z. So we would never try to calculate this by hand. way too complex, but you can see fairly quickly we can set up a study in SolidWorks that will calculate what's happening. And if we look at our plot, if we go to the results folder and re-show our acceleration plot, okay, so we've got this big spike again where the egg smashes into the ground, and then it tumbles around, and we got another significant spike where the egg tipped over and hit the ground on its side, and then it kind of slides along the landing pad, and we get another spike where it let's see, must have hit the ground or hit the side, but then it falls off, and we get another spike where it lands on its head down here, and then it tumbles around some more. And so anyway, lots of advanced motion analysis information we can get out of our motion study. Now, you're asked for your homework to turn in a screenshot of the egg motion analysis with the spring and damping coefficients listed on the picture. Just write in those coefficients if you want, and the screenshot should show the trace paths on the lander feet and the egg acceleration graph. So what you're going to want to do is have your trace paths, have your graph on the screen, and then you can just use the snipping tool to take a big capture of the entire screen, and then you can just use like this ink pen tool here, and you can just very crudely write in the values you use. So you can do like K equals 1, C equals whatever value you use. So just type or write those values in so we know how you define your suspension, and you would save this as an image file and submit that to D2L. So do you have any questions about anything in the motion study?
So for gravity, how come it was only acting on the egg and not the actual like body? Because I feel like if you press gravity, then it, like how does SolidWorks know that the moon or whatever should move?
Because this was fixed in space. In our assembly model, the moon was fixed, so it's not movable.
Okay. And is there friction on it too? Does that like include, or can you add that?
You can add that. You can, in your contact, you can add and define, you would use contact groups, and then you could scroll down here and define the materials and the friction properties, the coefficients of friction, whether it's static or dynamic, all kinds of friction properties. You could add that to your model as well.
Just like one more thing. Is that like changing acceleration? Because I noticed whenever the egg was falling, it was like, instead of the acceleration being negative, like, or is that just like really small? Instead of it being negative 9.8, it was like 0. I can't really see that.
Right, so the value we typed in was positive 1.62, where positive is taken as downward in the y direction. Right, so it's treated as a positive acceleration, but it's also very small, which is why it didn't show up on the graph very well. Okay, good questions. Any other questions? Okay. Now, what we're doing today, this is purely rigid body motion. So when the egg hits the ground, it doesn't deform. The legs of the egg lander don't bend when they hit the ground. Next week, we'll show you how to analyze deformable bodies, where you can actually apply forces to things and determine how much they deflect or how much they stretch and things like that. Okay, so the other package we want to look at is photo rendering. And I'm going to close as much stuff here as I can, because this is going to be a challenge for this computer. Keep that open. Close Word. Close that. Okay, when you open the Corvette model that I provided, it's going to say, do you want to proceed with feature recognition? And definitely say no on feature recognition for the car. Okay, so rendering in general is just a term that refers to producing a two-dimensional image of a three-dimensional object. And there's two popular ways of doing rendering. And this also usually shows up on the next lab exam as a short answer question in one form or another. But one way is called rasterizing. So with rasterizing, we're simply taking this three-dimensional object and geometrically projecting it onto a viewing plane. And that's what you're used to looking at in your SolidWorks models, as a rasterized image. It's very quick and easy for the computer, so when you're rotating or zooming in and out, it doesn't bog down the computer very much. But it doesn't produce very realistic looking images. You can tell that what you're looking at is like a computer model rather than a photograph. But rasterizing is also what they use a lot in video game graphics for the same reason. They don't want your video game graphics bogging down your computer. The other option is called ray tracing. So ray tracing is more like it simulates the actual physics of light. So with ray tracing, what the computer would do is shoot out a whole bunch of vectors from your viewport, or from your camera, essentially, and those vectors would bounce around. So when a vector hits an object, part of it would reflect, part of it would refract, keep going, but those vectors behave kind of like actual rays of light. And eventually, some of those bounces would send the vector back to the viewport, and that's what forms the image that you see. So a ray traced image is going to be much more realistic looking. It's going to look like an actual photograph. But the trade-off is much, much more computationally intensive. And so as we're working with these ray traced images, I think you're going to see that really taxing this computer. Okay, but once we have turned on our PhotoView 360 add-in, which we did at the beginning of the class, we now have this PhotoView 360 menu. And the first thing I want to do is turn on a preview window so I can see what I'm getting. If I do integrated preview, the whole display window here is going to behave like a preview window, and my computer is going to get very unhappy with me. So I recommend just doing a preview window and making it as small as possible. Simplify things for your computer. So here comes the preview window. Okay, so in the PhotoView 360 menu, let's look at this options button. So this lets you do things like specify the output image size and the image format that you want. Let's see. And then down below that, there's a section for the render quality. And you can set the quality for the preview window as well as the final render that we're going to produce at the end. Your options are good, better, best, and maximum. So this setting determines how many bounces a ray of light or a vector is going to take before it just stops calculating. So if we imagine that this cup was a clear glass of water, if you think about what a ray of light would do, when it comes in from the side, it would hit the side of the glass. Part of it would reflect and part of it would refract or bend as it passes through the glass. And then that ray of light would come to the next interface between the glass and the water, and again, part of it would reflect and part of it would refract or bend and pass through the water. It would come to this interface, reflect and refract again, come to the next interface, reflect and refract again, keep going. Part of those, some of those rays would bounce back to the viewport or bounce back to your eyeball to form the image you actually see. If we set the quality setting too low, what would happen is the ray of light would come in here and get partway through and then just give up and stop calculating. So the effect of that is it kind of creates like a black hole in your image. So if you ever see that in your image, that you just kind of have an area that just looks like it's missing, it's black, you may just need to come in here to your quality setting and set that to a higher level, okay? I'm going to go ahead and set this a bit higher for the final render. Okay, and then, let's see. Yeah, we'll go ahead and leave the other settings the same. Now let's see how we can put in a background image here. So if I go to the Photo View 360 menu and do Edit Scene right here, this allows us to browse through a library of built-in images and choose a background image. So let's see if we scroll down here. There's quite a lot that are built in. There's a conference room, there's a kitchen. You could put the Corvette in a kitchen. You see the microwave oven reflecting off the windshield and things. There's some outdoor landscapes. So you get to pick whichever background image you like the best. I'm going to go ahead and do the courtyard image because that's simply some tan and blue shading, and that's going to be easier on this computer to work with. So I'm going to choose that image and click Open. And it says the aspect ratio of the image and the camera are different. That's fine. Just click Yes, and it will adjust the aspect ratio as needed. Now you can actually import your own photograph. So if you wanted to go out and take a picture of the OSU library lawn, you could save that into the image library, and then you could bring that in, and you could see the Edmund Lowe Library in the windshield as reflection and things like that. So that's on the Basic tab. And let's see. Well, actually, let's see if we zoom this, rotate this a little bit. Okay. You notice anything weird or odd about the image as it was provided? If you look at the shadow we've got over here, it looks like the car is parked on its side. So, if you park your car like that, that's a bad day. But we can fix that by scrolling down here to the section of the Edit Scene box where you specify the floor, and you can say you want to align the floor with, in this case we want to align it with the XY plane. So I'll choose XY plane. And then you can also specify an offset. So if you wanted your object to be floating above the ground, you can just enter an offset distance. But when you align the floor with the XY plane, that'll get your car sitting on its wheels. And if you go to the Advanced tab, you have options like rotating the environment image. And then on the Lighting tab, you also have options for setting the brightness and the reflectivity. So if you wanted the car to look like it was all chromed out, you could increase the reflectivity setting. If you wanted to look more faded and kind of washed out, you could play around with the brightness and things like that. I'll just accept that for now. And, okay, in the homework, I asked you, let's see. Yeah, I asked you to produce an image using, I said to change the camera focal length to 24 millimeters, which means define a camera lens that's a 24 millimeter wide angle lens. So the way we do that is in our menus, we go to the View menu, and we go to Lights and Cameras, and we say Add Camera. Okay, so if I zoom out here, you can see here's the camera, and you could drag it around here, or you can just, I can drag this out of the way, you can just click in this window and zoom in to adjust the positioning of the camera, and you can rotate like you're used to rotating your models. But the camera lens options you have, or for specifying the field of view, are you've got some telephoto lens options. So that's like what they use a lot in sports, where the camera is way far away, but it looks like it's up close. But the effect of a telephoto lens is to kind of flatten out the image and reduce its perspective. The other option you have is a wide-angle lens, which does the opposite. It kind of increases the perspective and makes it look like whatever's happening is right in your face. It looks like a very dynamic image. So I ask you to use a 24mm wide-angle lens. Okay. And I'm going to see if I can rotate this and zoom in here. Okay, so if we look at the preview window, you see how it's just got a lot of perspective. The nose of the car looks like it's just right in our face. So that's the effect of the wide-angle lens, and to increase the perspective. And if you define that, let's see. Okay, if you define your camera lens and when you click the green check mark, if it looks like you lose the effect of it, which often happen like that, what you can do is go to the Display Manager tab of your Feature Manager, go to that camera, right-click on the camera you defined, and choose Camera View. Okay, so that just tells SolidWorks to make sure that camera is displayed in your photo view image. Okay, and then the last thing I ask you to do is add a directional light. So we do that by going to the View menu, Lights and Cameras, and we say Add Directional Light. And kind of like before, the light is right up here at the end of that line. We can drag it around to reposition it. But what I ask you to do is change the color to something other than white. So just click Edit Color and pick a color, whichever one you want. I'm going to do red. And maybe. Oh. Well, that's disappointing. All right, well. Okay, so I just got the blue screen of death there. It says your PC ran into an error, it needs to restart. So thank you, Microsoft. All right, well, what you're going to do is just choose that directional light. Thankfully, that was the last thing that you needed to see. And once you get it looking the way you want, to produce your final render, because all we were looking at was a preview window, you'll produce your final render by going back to that Photo View 360 menu, and there will be an option in there that says Final Render. Okay, so Photo View 360 menu, go to Final Render, and then it will produce a much nicer image. It'll take a little while, but it'll also give you a save button so that you can save that final image as your JPEG that you will actually submit to D2L. Okay, now, if your laptop struggles with this, just because it bogs it down so much, or it feels it like mine did, the computer labs are a great resource. The Engineering South Computer Lab has SolidWorks installed. You can do this assignment there. Some people have asked me, since the midterm, why did I ask whether we'd use the computer lab or not? The reason is because CIT is pushing to stop providing SolidWorks anywhere on campus. They want you to have it on your laptop, but they don't want to provide it in a computer lab anywhere. I've been trying to push to keep it in Engineering South, just as a backup for whenever your laptop may have problems or you need another place to use SolidWorks. But at the end of every semester, they say, well, how many students actually used it? Because if it's not very many, we're not going to bother to keep it installed. So that gives me data that I can send to CIT, and so that's why I asked. And if your computer has trouble, I encourage you to use the labs because it, the better, and I will ask that same question on the final exam.
Make sure the lights leave.
What's that? Say again?
We'll make sure the light leaves.
Okay, well, I can't encourage you to lie, but all I can say is the more people that use it, the better. That gives me more motivation to see that CIP should keep providing it. Do you have any questions at all about anything?